Hi there, how is everyone doing? Today we'll look at the Perceiver General Perception with Iterative Attention by Andrew Jägel, Felix Gimino, Andrew Brock, Andrew Scissorman, Oriol Vinyals, and João Carreira of DeepMind. This paper on a high level describes a model called the Perceiver, and what this model does is it interleaves a latent self-attention mechanism with cross-attention mechanism. And so it is a transformer, and the secret is that the data only enters the transformer through this cross-attention mechanism. That allows the model to have the latent array be of significantly lower size than the data array, and this solves in part the transformer's quadratic memory and compute bottleneck. The image comes in, or the data rather, comes in multiple times through this stack, and the weights can be shared, making it essentially a recurrent neural network. This model here works for any modality. So the paper not only does images, but videos and audio and point clouds, and you have to change pretty much nothing about the input in order for the model to work. So this is a pretty big step towards, first of all, making transformers more deep, and second of all, applying the same models to very, very different modalities of data. So we'll dive into the paper, we'll look at how it's done. It's actually a fairly simple idea, so shouldn't take us too long. I always say that, but maybe today we'll achieve it. If you like content like this, tell me how you feel in the comments, leave a like, tell your friends about it, and let's go. So they motivate the name. The name Perceiver, it's not really tied to anything. They motivate it by saying biological systems understand the world by simultaneously processing high-dimensional inputs from modalities as diverse as vision, audition, touch, proprioception, etc. The perception models used in deep learning, on the other hand, are designed for individual modalities, often relying on domain-specific assumptions, such as the local grid structures exploited by virtually all existing vision models. So what do they mean? They mean if we have an image, and the image is of not a cat, a house. What did you think? So the image is of a house, and if we have an image processing pipeline, usually what it will do is it will assume that the image is some sort of grid and that you can localize any pixel by its XY coordinate, and also that the pixel is in some kind of relation to the pixel around it. We usually build models according to that. So a convolutional neural network very explicitly will slide over a filter over the image with all shared weights, and therefore it directly says that what matters to a pixel is the pixels around it, and only in the upper layers and after some pooling do these receptive fields grow, such that more and more information across larger distances is incorporated. On the other hand, something like a visual transformer, like the VIT, what it will do is it will do transformer-like attention, but because it can't, because the images are so large, because whatever 224 by 224 pixels are just too much to put into one transformer, it will simply subdivide the image into these patches, and therefore it also essentially says it will take each patch and make a vector out of it. So it also essentially says that whatever pixels are close together, they go into this one vector. So they're treated as a group. So this paper says that all the current architectures that deal with computer vision somehow have this built in. However, So other models have that too, other modalities like audio, video, and so on. And the perceiver here is supposed to alleviate that. So they say it induces helpful inductive biases, but also lock models to individual modalities. In this paper, we introduce the perceiver, a model that builds upon transformers and hence makes few architectural assumptions about the relationship between its inputs, but also scales to hundreds of thousands of inputs like convnets. So transformers, notably, are models that transform sequences to sequences, or let's say sets to sets. So you have an input set, and what we've usually come to know as transformers are stacks of self-attention layers. And in the self-attention layer, what you would do is you would simply transform the input into an equally length output sequence, and in the middle you'd have this attention mechanism, and the attention mechanism essentially needs to compute the weight between every one of the inputs and every one of the outputs, giving rise to an O of, let's call that M, I think they call it M squared. So here you have M sequence length. So an O of M squared compute and memory requirements. Now, if M is small, that's not a problem. But if we go into the range of NLP, usually, so in NLP, we usually deal with M's in the order of, I don't know, 2,000, 1,000, let's say 1,000. So in the order of 1,000, though we would want more ideally, but in the computer vision, our M is easily something like 50K, which is about 224 squared. So the M squared would be 50,000 squared, and that just blows the memory of our computers. Maybe not the ones in the future, but certainly the ones now. All right, so the problem here is that these transformer architectures take too much memory. What this paper does is it goes ahead and it says, couldn't we do a better job? So usually in a transformer layer, I'm going to draw this again here as two layers. What you'll do is you'll compute queries, keys, and values from the same input. So you have your input right here. And what you'll do is you'll compute queries, keys, and values from that input. And those get mingled together in the attention. And that gives you the next layer. And you'll produce queries, keys, and values again. Queries especially are of size M by D. Keys are also of size M by D. Now, if you multiply those two together and you transpose this, you can clearly see that gives you a matrix of size M by M. What this paper does is it says, okay, we can draw back actually on what the very initial transformers proposed. The very initial transformers, if you remember, and if you don't, you can go watch my video on it. The very initial transformers were something like generative models that had an input sequence and they had an output sequence. So the output sequence, and maybe that wasn't fully completed yet, right? So you want to predict the next thing. But there was a clear distinction between sequence A and sequence B. Now, sequence B would do self-attention. So they would have these stacks of self-attention layers with the quadratic thing, and ultimately you'd want some kind of output here such that you know what the next word would be. This is sort of an autoregressive model. However, the input did not use self-attention, it used cross-attention. So it was also a stack, but it used cross-attention, so it went sort of like this over. And the way that works is, so by the way, think of machine translation, right? So here is the German sentence, and here is the half-finished English sentence that you would want to complete. So if you want to know what's here, you need to attend to the English sentence. So every part of the English sentence needs to attend to the English sentence, but also every part of the English sentence needs to attend to the German sentence. That's why you have these paths going over. But none of the German sentence necessarily needs to attend to the English sentence. It could make sense, but it's, it's a restriction where you say, okay, the information flows from the German sentence to the English sentence. So, and that results in this cross attention, where the keys and the values are produced from like sequence A, but the queries to do the cross attention, so the queries for this particular flow of information, are produced by the target sentence. And you'll notice something. These now can be of different lengths. Notably, if the sentence B right now is much shorter than the sentence A, that would result in a shorter queue, and that would result not in an M by M here, but that would result in like an M by something smaller, right? And let's call this N. And if N is much smaller than M, then you don't have this quadratic bottleneck. So that's exactly what this model does essentially. Let me just get rid of all of this stuff again. This is akin to a few things. So it's akin to the original transformers. It's also akin to, if you remember the model DETR, which is a detection model. And what we call the things there are learned queries. So what do we do here? We start with, our goal is to have a latent array that is not huge. So N here is a size that we can handle in a regular transformer. And this stack, the top row here, is just a regular self-attention transformer with all the drawbacks. But because we only have sequences of length n, the self-attention modules right here, so this is latent transformer, this is classic self-attention that we do here, and in all the stacks, in all the layers to follow. But we can handle it because n is relatively small. So in this paper, I think n is something like 500 or 1,000. It's something you can handle with current hardware. The problem is when you want to bring in an image. But this is quite smart. What do? They take the image and they just unroll it into a byte array. So now we have the M here, and the M is huge. The M is 50,000. However, because we produce the queries from the latent array and not from the image itself, we won't get the quadratic blowup. So this is M and this is N, and you can see that results in an N by M attention matrix and not an M by M attention matrix. So in this cross attention module, the data of the image comes into the latent, into the transformer. However, it is not transformed into an equally long sequence. It is transformed into a much shorter sequence, namely this latent state. On this latent state, we have a transformer, transforming it into a new latent state. From that, queries are generated to do cross-attention again to the same image. So the same image will come in every single layer. The same image will come into the architecture, and so on. So if this reminds you of a recurrent neural network, that it is sort of a recurrent neural network, especially because they say you can also share these weights between repeats. If you share these weights, it is definitely a recurrent neural network, where this here is the initial state, which you either learn or randomly initialize. In this case, I'm pretty sure this is learned, though I might have misread. So this concept, again, it relates to RNNs. In fact, it is an RNN if you share the weights. It relates to learned queries as opposed to generated queries. So you can learn the queries instead of generating them. When you learn them, you can choose yourself how many there are. And it also sort of relates to, I'm not sure, but how to call this. You can see the image goes in multiple times. So the way conceptually you can think of this is that here is a bunch of learned queries. They have no clue about the incoming data. So what you generate here is just kind of a generic set of queries. Like, what would you know? What would you like to know about this incoming data point? And you have 1,000 things that you can want to know. And you have, 50,000 things to attend to. So you're going to choose 1,000 criteria, right, to gather from that input data. Now, the way attention works, right, is the queries. You have a set of queries, Q, and you have a set of keys down here, a bunch of keys, more than queries. And every query exposes sort of a vector, and every key exposes a vector. And the information is routed by means of highest or high inner product. So you would route things that have a high inner product together, like these two. Yeah, those are the ones that you would route. So every key potentially has not potentially, every key has a vector associated with it. So the queries essentially say what kind of things I would like to know of the incoming data. And the keys are, say, for each pixel in the data, say what kind of things that particular pixel offers to the model. If you just do this once, you might get some generic information, but then you get to do it again. And you will notice that the queries here, the later queries, are a result of that processing. So the data comes through here, right, and influences these next queries. Therefore, these next queries here can be dependent on the earlier data. So you can pretty easily see that, now the next time you're going to attend to this data, you do this in an informed fashion. You already kind of know what's in there. So you refine what you would like to know about the data and so on. You can refine and refine. You can ask for more and more specific things the more you learn about the data. So this is really a process of learning more and more about the data in a dynamic way where you can say what you would like to know. And, this, I think it's a great idea. It might be refined in the future, but it certainly does also, it makes sense. And it also solves the kind of quadratic bottleneck. Oh, wait, I almost forgot. I had a visual demonstration of how the quadratic bottleneck here is solved. Bear with me. Here's a matrix. It's m by m. Now watch. Problem solved. All right. So, by the way, the lower is supposed to represent n by m. I did not write that down. Okay. So this not only allows you to overcome this quadratic bottleneck, it also allows you to build much deeper transformers. So I believe their best architecture here had 48 layers of transformer, which we can do in kind of NLP, but it takes a lot of hardware. And when they also share the weights, their number of parameters in these things is not more. I think it's comparable to kind of a ResNet, a standard ResNet. So yeah, pretty cool. So they apply this to pictures, they apply this to videos, they apply this to audio, they apply it to video and audio together, they apply it to 3D point clouds. Though one has to say for video, they don't actually put the entire video into, so this here isn't the entire video, but I think they also put kind of little time-space chunks of the video in it. So it doesn't solve yet all the problems with transformers. It's still, if a data point is huge, you won't get it in there simply by the fact that it's linearly huge. What you will solve is the fact that things are quadratically huge. The last thing to do is to pay attention to this thing, positional encodings. Now, the way they do positional encodings is, so now we have like a fully independent, like a data modality independent architecture, right? It's important to realize this. This thing here has nothing to do with an image. Like, is it an image? Who knows, right? We don't care. This is the array of pixels. This is simply the unrolled image. There is no convolutional filter. There's no patching or batching or anything. There's just the image, or it's the audio data, right? It's like sample after sample of audio data, and so on. This you can even think of a situation where you would feed in different parts of the data from time step to time step, in which case it really becomes like a recurrent, just like a recurrent neural network. But the point is, the transformers, they are invariant to position. So if I feed 1, 2, 3, 4, 5 into a transformer, it will do exactly the same thing as if I feed 3, 1, 2, 4, 5. That is not much of a permutation, but it is. So it is invariant. Now that stifles it, because there is something to something being in a certain location, right? Especially if you think of text, word order matters, and so on. But there's a clear distinction. We don't want to build these things into the architecture, but we want to give the model the possibility to exploit that information, because clearly it's there. Like, a piece of text is not just a set, it is an actual string of ordered words. So what do? We give positional encodings with the input. And positional encodings, have been used all over the place. Transformers specifically need them. The way this paper does positional encodings is like they do it, or much like they do it in the first transformer paper, and that is by Fourier features. So if you have 5 inputs right here, you build up kind of a Fourier bank of frequencies. So this is the lowest frequency, something like this, like a sine wave, and then a higher frequency. Well, 5 probably wasn't the optimal thing to demonstrate this. So by kind of indexing, so here, if we look at the position number 2 right here, it has like, if we just consider this binary, it has like, no, not binary, like high, but like 0.9, 0.9, -1. That's kind of the encoding. That's the positional encoding of that location. And if we look at 3, it's 0.9 -1, 1. So you can see that you can, with this kind of positional encoding as opposed to a learned positional encoding, what you can do is you can always detect when 2 things are close together. That means that in the lower frequencies they will share the same number, and you can also do very high resolution. You go to the highest frequencies, and if they're different there, but if they match all of the frequencies above them, that means they're like right next to each other. So that's how you do position encoding with Fourier features. Again, I discussed this at length in my Attention is All You Need video. The Fourier features also have the additional benefit that you don't rely on learned encodings, which means you don't rely on the fact that you have kind of an exact or a maximum amount of sequence length. So you still have kind of a maximum here, but I like this more because it's sort of independent. It's one less thing to learn, and the learning happens in the processing itself. So in terms of experiments, it's pretty simple. They are in vision. They are on par with something like a ResNet 50, and they're doing pretty well in vision without any sort of assumption that the input data is an image, right? That's the crazy part. So other than the position encodings, which are the Fourier features in 2 dimensions, there is nothing here saying this is an image. It's simply an array of pixels. I think that's crazy. And sorry. This is visualization of the attention maps. So in this model specifically, what they do is layer 1 has a set of weights, then layers 2 to I think 7 have a different set of weights, and then layer 8 has another set of weights. So layer 1 is the blue here, layer 2 to 7 share the weights, they're green, and the last layer do I have orange here? Okay. And you can see that these are the attention maps of different channels. And they stress that they don't overlay it on the image. So the attention map in the first layer actually really attends to the image pixels. You can see the dog clearly in many of these attention maps right here, like where it attends to. Clearly attends to parts of the dog, and it seems that it can do sort of edge. No, it kind of attends to the intensity of the pixels, right, in the first layer. Then in the second to seventh layer, attention maps look like this. So they look like sort of a grid. So they heavily rely on these positional encodings in order to build up this grid. However, this grid is not always the same. It's sort of different for different things. And then in the last layer again. My question would actually be how I see that these things are different from channel to channel. So these are the different channels right here. But how different are they from input to input? Like, has the model just kind of learned a general sequence of attention maps for all possible input images, like that it works well? Because it's kind of suspicious, right? That these maps, they seem... So my question would be, how much do these attention maps really depend on the input versus how much are they just general attention maps, right? And so I can totally see that this model might just do all the work in the latent transformer by simply having so many layers, and that the attention isn't too important. Like it would always do the same sort of attention no matter what the input is. And I can see a model like that totally performing well. So in order for me to demonstrate that this idea really works as advertised, namely that the model selects itself what it wants to attend to, iteratively informed by the data and so on, it would be cool to see that these things somehow depend on the data, because this grid pattern right now tells me that maybe they don't. Okay, so the last thing, they also apply this, as I said, to audio, video, 3D point clouds, and I think they outperform other methods in these. So they reach state of the art in a bunch of them, which, pretty cool. Of course, image computer vision has been sort of the prime, or one of the prime disciplines of deep learning research. So that's maybe a bit more competitive. Last thing I want to show here is the ablations. So they find specifically that the number of latent variables, which is the size of the Q, the n. So this is what we need to keep small in order to avoid this quadratic bottleneck. You can pretty clearly see that as this goes up, performance goes up. So this at least validates our intuition that if we could do bigger transformers, it probably would be a good idea. Number of attends, I think that is how many times the image goes into the structure. Also here, the more the better. And number of transformers per attend, that's how many in between self-attention layers do you have per time you attend the image. So that gives your model time to process and time to decide what to attend to next time. Also here, we see a rise, though it would be interesting to see like an interaction term between these two things. That would tell us if it's just about making the model deeper or not. Okay, so that was all I had to say. You can kind of check out the attention maps they have here themselves. They have them for audio. They have them here, I think, for the video. And also, there are a bunch of experimental details that are also pretty cool. However, I just think it's a cool idea, and I'm excited to see where people take this. All right, that was it from me. I'll see you next time. Bye-bye.